Hi everyone and welcome to another lecture of Digital Design with Verilog course. Okay, so today we will discuss about signal strength and nets. So let's start with signal strength. So I briefly told you about strength levels. I told you we will understand this later. So today is the time, right? So don't worry if one of the term is unknown to you now. Tomorrow it will be known to you. Trust me, I will cover each and everything. But obviously I cannot cover everything in a single video. I have to go step by step. Okay, so let's start with this. Strength levels. What are signal strength levels? So you can assume this as a second type of data type. First data type was the value 10x and high impedance. This is the data type 2. Okay, so what is it? Strength levels in Verilog describes the driving capability or storage capability of signals on a wire. Okay, so obviously I will explain you, don't worry about that. This is particularly important when multiple signals are driven on the same wire, as signals with the stronger strength will dominate. So what do I mean by this? Okay, so if I have a supply, this is VDD, just hold on. This is VDD and this is ground. Okay, VSS, ground. I have two wires. So if I want to connect like this to a, this is wire A, if I want to connect this one and connect this one, which one will win? Which one will win? So to remove this ambiguity, right? To remove this ambiguity, we have a solution that is known as strength levels. So basically, if two wires are driving, like if two levels or two different things are driving a single wire, then we choose the variable with the highest strength. Whichever has the highest strength, that will be used. So these are the strength levels. Just remember that, no need to remember too many names, but try to have a feel of the names. Supply, as the name suggests, it is for supply. So hence it is the strongest, right? Supply can have two values, supply 1, okay, supply 1 or supply 0. So anywhere if there is supply, of course, now you might have the doubt if sir, two same strength are there. If this is supply 1, if this is supply 0 and they are connected, then obviously again it will be cross unknown value. If different strengths are there, then the highest strength wins. Okay, simple as. So supply is the highest strength, then we go lower, strong, then pull, large, weak, medium, small, high impedance. Also they have different type of use cases. What does driving means? Driving means I will drive a wire, right? Or I will drive a wire, like the wire can be driven to high or low. I can drive a wire, okay, drive a wire on net data type also we'll understand today. Okay, so strong, these are all used for driving purpose. This large, right, is used for storage purpose. Storage means this will be used in rich, this will be used in rich. Okay, this medium is used in rich, this is used in rich, and high impedance is high impedance. This has the weakest strength. Whatever, like high impedance means it is floating, right? Whatever wire will connect, it will automatically pull to that wire. If it is 0, it will pull to 0. If it is 1, it will pull to 1. Simple, high impedance, right? So now let's discuss more about these things. So driving strengths are associated with signals that actively drive a wire. Examples: supply, strong, pull, weak. These are all the driving strengths: supply, strong, pull, weak. Okay, and other are storage strengths. I will explain that as well. Storage strengths are used for signals stored in tri-reg nets or reg. Okay, I will explain tri-reg net is not inside the syllabus, so we'll ignore this. Okay, just you should know this fact that it is used for tri-reg nets. Okay, we'll ignore this for now. It is not inside our syllabus. Then high impedance. High impedance, as the name suggests, it represents a state where no signal drives the wire. It can easily be driven, right? If anything is connected, it can easily be driven. That's why it has the weakest signal strength. Okay, now these are the rules of signal contention, right? If two signal strengths of unequal strengths are there, okay, like let's say one is supply, then I have pull. Okay, so which one will win? Supply will win. Okay, so the signal with a stronger strength prevails. Examples: if strong 1 and a weak 0 are driven, right, to a same wire, then the result will be strong 1. Strong 1 will win. Okay, if equal signals are there, if two signals of same strength are like driving, then the result will be unknown. as we have known from the previous lectures as well, result will be unknown. Okay, if strong 1 and strong 0 are driven, result is x. Okay, so if strong 1 and weak 0 is like driving this wire, then result will be, what will be the result? Result will be strong 1. If strong 1 and strong 0 are driving, the result will be x. I don't know, result is unknown. Okay, of course in real life there will be some value here at this node, some voltage will be there, but in simulation the value will be x. It is unknown to me, something has gone wrong. Okay, so what is the application of this signal strength? Of course you know, right? If multiple signals are driving same wire, it helps us resolving the conflicts. It helps us resolving the conflicts. That is what is written over here. Strength levels are essential for resolving conflicts when multiple drivers content on a single wire. Basically they fight for a single wire. Okay, modeling of MOS devices used in low level design to accurately simulate MOS behavior, because few MOS, right, it has high pull up, high pull down. If you have heard about this term, then you will understand what does high pull up means, what does high pull down means. Okay, it is used in dynamic circuits. So like these are the use cases. Okay, we will come to the code, don't worry, we'll come to the code. So if I come to the code, right, I will just go to the code quickly. So I have opened my code in the VS Code. Again I have to do every step from the starting. Again I have to do cd because I have changed my file. So I will copy my location of this file and do cd and paste this. Okay, so I have done cd, I have got into my location. Now what I will do, again I will do iVerilog. Okay, iVerilog, but the names will be different, right? This, right, is the test bench and the names are different. So this names will be net test check VVP. Okay, this will be the name in which the output will be stored, and this will be the name nets check the test bench. That will be the code that I will compile, and in turn test bench will call the different modules. So these are few modules which I have made. First module is this one, wire strong weak check. So if I have a strong 1 and 0, like assign, like this is how we used to assign, like the strength is written like this, strong 1 0. Okay, so this x, right, has a strength of strong. It can be either 1 or 0, but we have defined here 1, so this will be strong 1. That's it. Okay, and I'm doing the same thing again. I'm assigning weak 0. Okay, I'm assigning strong 1 and weak 0. Which one will win? What will be the output of x? I will then I'm assigning b to x, and then I'm printing. So I want to see which one will win. Okay, so I'm assigning the same wire two different values but with different strengths. Okay, this is just for defining the strengths, like what is the strength of 1, what is the strength of low. Okay, I can write here weak 0 as well, no problems. So then if I write 0 here, then the signal strength will be weak 0. That's the only thing. Okay, so now if I compile this code, so I will compile this code. It is okay, something has gone wrong. Okay, some weird thing has happened. Then if I do VVP this, okay, VVP this, let's check VVP. So yeah, it is telling output of the net is Z. Why is it Z? It should not be Z actually. Why is it Z? This is wire B, wire strong weak check. I'm assigning x to 1 and 0. Should not be Z actually. Yeah, sorry for the interruption. I was making a mistake, like I was like putting this name wrong. So now this name is correct. Now I will press enter, and then I will see the output, right? See the output from this. This will be VVP. Now if I check the output, yeah, now it is showing me the correct value, that is B equals to 1. Okay, so this one wins. This one wins. Okay, now if I write here weak 1, okay, if I write here weak 1 and this as strong 0, now who will win? Now if I recompile it, you see 0 has won, right? So it's not like I have to like assign the same strengths here. I can assign a different strength as well. Okay, but you have to define what is the strength of 1 and what is the strength of 0. You have to assign that. Okay, that is the most important point. So now I hope you have got this logic. Okay, I will change this. What was there previously, I will change that. Okay, so this logic is done. Now let's check for the high impedance state. Okay, let's check for the high impedance state. So if I check for the high impedance state, So by default, right, wire is initialized with Z. If it is not connected anywhere, so it will be initialized with Z. Now if I want to call this module, right, if I want to call this module, I'll call this module here. Okay, again I will recompile it. So if I recompile and call it, so you see I have not initialized anything, so wire is initialized with Z because it is high impedance, it is not connected with anything. Okay, now if I do something, assign 1Z, again we are driving it like high impedance, so it will be high impedance only. Okay, nothing will change, it will be high impedance only, it will be high impedance only, you see, high impedance. But now if I assign, even though this is a strong 0 and 1, right, but it is high impedance only, so it will fail. We are driving some value, hence the net will go out of the Z state, that is the high impedance state, because whatever value, it doesn't take care of the strength, it just check some value I am driving, it will go out of the high impedance strength, high impedance state. Okay, so again if I recompile it, you will see it has gone out of the high impedance, it is now equal to 0. Okay, so that is how we will check like this. Now let's call the strong. Okay, strong check. So if I just copy this module name and instantiate this module here, what is this doing here, right? We are driving the same thing, we are driving strong 1 and strong 0. Okay, so output will be X, as both are driving with similar strength, output will be X. We have learned this theoretically, now we will see this practically. Okay, so I will again rerun this code. If I rerun this code, you can see it is X. If I somehow comment this one out, okay, then rerun the code, it will not be X, it will be the value 1. Okay, it is the value 1. Okay, so now if I uncomment this out, this will be value X. So now I hope you understood, if they are same strengths, then the value will be X. Okay, so next this examples I will come to, don't worry about this. This is after the nets example. So I hope you have understood about the this signal strength. Okay, now I will show you the tablet, and now we will discuss about the nets. Okay, we will discuss about the nets. So if we discuss about the nets, what are nets in Verilog? So nets represent physical connections between hardware elements in digital circuits. Okay, so that is what nets represent. So basically it is just like wires, they are continuously driven by the output of devices they are connected, and they are connected to and reflect the real-time values. Basically these are wires. Okay, that is what nets are. Okay, like many places, somewhere it is written net, somewhere it is written wire, so you get confused, that's why I have taken this separately. Continuous values, nets have values that are continuously determined by the drivers connected to them. So I can drive 1, I can drive 0, or this A net is getting driven by this G1 gate. Okay, remember net always needs a driver or wire, like this also you can say as wire. If nothing is driving, right, it will be high impedance state or floating. Okay, tri-reg you can ignore for now. Okay, so all this, right, are all nets, all these are nets. Okay, so the like how do we declare nets? It's same as wire, it is just wire. Okay, so we declare nets with wire. So this is a single bit wire, this is used to declare multiple wires, right? Like if I want to declare 3 wires, I will not write wire B, then wire C, then wire D, not like that, right? It will be so much waste of space, so I will directly write wire BC. Okay, together I can declare many wires. This is interesting, try to understand this. What is this? This is a 4-bit net. Okay, also known as vector. Don't worry, we'll learn about vector as well, it will come after this. So this, right, is what this here is 4 bits. Okay, 4 bits. So basically what we tell, this is the MSB and this is the LSB. So how can you calculate the number of bits? You will do this simple calculation, MSB minus LSB plus 1. Why this plus 1? Because you have to take into account the 0 as well, that is only reason. Okay, so here it is 3 minus 0 plus 1, so it will be a 4-bit number. Should I count the number positions? So this is 0th bit, this is 1st, first bit, 2nd, 3rd bit. Okay, 4-bit number, that's how we represent a wire, 4-bit wire. Basically the 4-bit wire, right, will be something like this. Here I will have 4 bits. Okay, this will be my D, this will be my D of 0, like you can use it as array, right? D of 1, D of 2, 2nd position, and the MSB D of 3. Okay, so you can define this as a single wire as well. You can write it like this slash, okay, and then say 4 bits, then say 4. Automatically people will understand this is a 4-bit wire. That's it. Okay, so that's how we declare wires. Now, class of data type. While net is not a keyword, it represents a class of data type, because like although I told you that net and wires are similar, but wire is the most commonly used. Net has other class of data types as well, like WAND, WAR, tri-reg, supply 0, supply 1. These are all different class of data types. Okay, so what is WAND, WAR? I will explain that in the coming slides. Don't worry about it. So if it is if it has a no driver, it will be simply high impedance. Okay, so yeah, let's understand few things. This is a single bit wire, very simple to understand. This is a multi-bit wire, right? If it is a 4-bit, data is 4-bit, then I have to give the 4-bit input. So basically it is a 4-bit data, right? This is data. So this is the LSB. Like you can write anywhere you want, like there is no standard convention, so I am just writing this as LSB, this as MSB. So this will be 1, this will be 0, this will be 1, this will be 1. Okay, this is 1 by DEs. Now next is modules. Example 3, wire is ABC, assign BC. Okay, so here, right, it can be driven by a gate output, like as like this gate, right? Whatever I was explaining here, this. Okay, I can call this gate, and this gate is driving this wire C. Okay, sorry, not C, sorry, net A is driven by the output of the AND gate B and C. That's it. Okay, output is driven by this B and C. That's it. We can drive it. So these are all examples of nets which we already have studied. Okay, so these are the common net types and their description. What they do. Wire is just standard wire. That's it. Okay, wire is just standard wire. What is WAND? WAND is wired AND. Okay, don't worry, I will explain what is wired AND. I will explain that. It basically inserts a AND gate whenever there is multiple drivers. Okay, I will explain that. WOR is wired OR. Tri is 3-state tri-state. This is not in our syllabus. Tri-reg is also not in our syllabus. Supply 0 is simply constant 0 net. Supply 1 is constant 1, or like you can discuss about different strength levels as well. Pull 0, pull 1, weak 0, weak 1. Those are also net types. Those also I will come to. Don't worry about that. Okay. So wire is the most commonly used. It just represents a simple connection. Multiple drivers can cause signals to shorten together. Okay, so basically if there are multiple drivers of same strength, then they can be shorted, right? So to resolve this, we use WAR or WAND. We generally don't use these things, but still we have to learn. In Verilog we have to learn everything. That's why. Okay, so what is WAR? WAR is wired OR. It inserts an OR gate when multiple drivers are present. Okay, it basically inserts an OR gate when multiple drivers are present. Okay, so don't worry, we'll do this. Resolves multiple driver problem with a logical OR, and it inserts AND gate. We'll come to this, don't worry. These are also, like as I mentioned, Verilog different strength levels. This is also a net type. Okay, this has already been covered. So these are few examples of net data type. I have already taken these examples, right? These examples have already been taken. These have already been taken. These are already done. Okay, so I've already explained these things. Okay, so let me just remove few slides because those are not required. This is not required. This is also, yeah, this is required. Okay, yeah. So now let's come to this WAR and WAND. Okay, so let me come to the hardware and then explain. Okay, not hardware, sorry, let me come to the code and then explain this. So I will just quickly turn on my code. Yeah, here is my code. So let me come to the WAR case, right? So this is the case. So let me uncomment this and let me call this module. Okay, let me call this module here. Before compiling it, let's understand the code. So output is B. I have defined a net of WAR data type whose identifier is X. Okay, I'm assigning it a strong value of 0. Okay, then I'm assigning a weak value of 1. So what it will do, it will not think about the levels. Okay, it will just do a logical OR. Okay, you can change the strength levels, it will not take care of the strength levels, it will just do a logical OR. That's it. So let's compile this. So what output am I expecting? I'm expecting a 1 output because 0 or 1 is 1. Okay, So now if I do I Verilog and then compile, I'm expecting 1 and I have got 1. So now if I do this as 0, okay, even though strong is 0, right, strong is 0, so if we would have gone by the strength logic, then I should have gotten the output as 0. But as it is a VOR data type, that means it is just simply doing the OR of 0 and 1. So I am getting as 0. That's it. Okay. So here, if I do a pause in this video, so like let me just change this to 0. If I change this to 0, okay. Now if I again compile this, if I compile this again, you see I am getting a 0. It is just simply doing OR. It does not think about the strength. Okay, you can play around with strength, you can do strength anything. Okay, you can do the strength anything, it will not change anything. Okay, so yeah, that's what a VOR does. So I'll just again comment this one out. Now let's go to the next one. If it is high impedance, okay, so again I will copy this module, paste this here. So now what we are doing here is we have a VOR data type, and first of all I'm assigning Z. By default a wire is always initialized with Z, right? If I don't do any assignments here, okay, if I don't do any assignments, and if I now check the output of the net B, you will see by default it is high impedance Z. Okay, now like this is already assigned to Z. Now I'm assigning it as 0. Now we are driving it as 0 Z, so net is not terminated with Z, hence we will get 0. So because now we are not in high impedance state, I am driving it something, so now I will get the output as 0. So if I want to compile it, see I am getting output 0. Now again if I assign it 1, okay, even if one of the drivers become 1, it will always be 1, because simply it does OR, right? It does OR of everything, right? So it will do OR. Again the output will be 1. Okay, I don't care, it doesn't care care about the strength levels, it just simply does OR. Why is this used? Just to, again, another way to remove the conflicts, right? If multiple drivers are there, to remove the conflicts, this is one of the way. Okay, this is just a simulation thing, that's it. Okay, so let's now move on to the next one. So if I move on to the next one, this one. So this is VOR strong check. So if both are strong, okay, if both are strong, then also it doesn't care. Like previously, right, what we should get if it's simply a wire data type. If I just choose this, a wire data type, okay, this is just a wire data type. Now if I compile this code, okay, I have to copy this module name and paste this over here. Okay, and if I just simply compile this code and run, I'm getting a X, right, because I'm driving the same strength. Okay, now if I change this to VOR data type, so that is why this is like useful to us. If I change this to VOR data type, it will just simply do a OR. Okay, it doesn't care about the strength, simply does a OR, that is 1. Okay, so that's the advantage of this. That is the advantage of this, right? Here, even though there is an assignment of X, right, it ignores the assignment of X. Okay, it simply does, whenever there is a one logic 1, it will follow that one only, it will follow that one only. Okay, it doesn't take care. So I hope you have understood the use case for VOR. Okay, let's come to the wind. Wind is wire AND, so simply it will do AND. Okay, same thing only, same things, you can try it out by yourself. Okay, it will ignore the strength levels, it will just simply do AND. Even if one of the drivers is 0, everything will just become 0. It just has a logical AND connected to before the main wire, right? So if I compile this, it will just be 0. Okay, it will just be 0. Same for the next few modules as well. This is the same thing again, and this is the same thing again. I will not go through this. Just we are doing the same thing again. We're doing the same, nothing different we are doing. Okay, so you can play around with this code. This code is obviously there in the PDF. You can play around with this. So I hope this point got cleared to you guys. Now what I want to do, I will give you a few questions and I want you to solve those questions. So these are the few questions, right? So like I have explained the code. Now I'll give you a few questions. Before that, just wanted to say about the difference between nets and variables. So default value in variables like reg, right? Reg, and this is like var. Default value in reg data type is X, unknown, but default value in nets is high impedance, because net is not connected and reg is just a storage value. We don't know what value is there in reg, that's why it is unknown. Okay, and it has to be driven continuously by a hardware driver. Someone has to drive it, like a supply, like a ground, or a drive, or a MOSFET. Something has to drive this wire, right? But this doesn't need any driving, just need to get updated once, either 1 or 0, something like that. Usage, it is used in physical connections, it is used for temporary storage. Okay, for computation it is mainly used in simulation, and it is actually used in hardware, physical hardware. Okay, showing the interconnections. Okay, so now what I want you to do is try out these questions. Okay, pause the video and try out this question. I will show you the question one by one. This is the question, this is the question, this is the question, and this is the question, and this is the question, this is the question. These are all questions. Try out, pause the video and try out all the questions. Okay, then I will solve all the questions. Okay, 12, 13 and 14. Yeah, that's basically it. This is the last question. Okay, this is the last question. Pause the video and try out the questions by yourself. Now I will solve all the questions. So let's start with the first question. Okay, so what is the default value of a wire if no driver is connected? Like, this is very simple. It will be high impedance, right? If no driver is connected, basically it is floating, so hence it will be high impedance. This has been explained multiple times in this lecture only. If two drivers drive a wire with same strength but different values, 1 and 0, okay, but they are same strength, what will be the final value of the wire? It will be simply x, right? It will simply be undefined or x. Okay, so again, very simple. We have done this example in the coding itself, right? Let's do the next one. This one, which type of models net type models a wired AND connection when multiple drivers are connected to it? Basically, in the wired AND, right, I have this wire. Before connecting to this wire, I have a AND gate. All the different drivers are first ANDed first, then the output is given here, right? So it is wired AND, right? Very simple, not that difficult. Like, these are all simple questions only. So taking a few simple questions, okay, so that you are involved in the lecture itself. Okay, so let me delete this thing as well. Let me delete this thing as well. Okay, yeah. Which of the following nets default to supply strength levels? Okay, so is this a supply strength net? No, these are all, this is like tri type, this is wired, or this is wired. This is the supply strength net, right? Supply one. So this will be the default supply levels. Okay, so let's move on to the next question. Again, I have extra slide. So this question, okay, if two drivers with different strengths drive a wire, which signal will dominate? The signal will with higher logic level. Okay, now there are different strengths. Okay, which signal will dominate? The signal with higher logic level, 1 greater than 0. Like, if it is at high logic level, will it dominate? The signal with higher strength, the signal with longest duration, undefined, it will be the signal with the higher strength. Okay, very simple thing that we are studying in this today's lecture only. Okay, so let us solve another like basic question, coding snippet we have. So in this question, the snippet is given. Okay, and like this we have done in the coding itself. What will be the output? Basically value of x. So here I am first assigning it a strong 1 and weak 0. So output will be simply strong 1. Okay, higher strength will win. Okay, we have already done this question only, so no problems. So let me delete this. Again here, now this I haven't told you, right? Consider a VOR net driven by two signals with different strengths. Okay, what will be the output? So I don't care about the strength, right? If I have a VOR net type, then simply I will take the OR of these two. Even if one of them is 1, output will be 1. So it will be simply B1. Okay, as it is a VOR data type. Okay, so yeah, not that difficult to understand. Okay, so let's come to this one. Let's come to this one. So which of the following represents a legal assignment to a supply 1 net? Assign week 1, week no, I want to assign supply 1 net, right? So this is the legal assignment, supply 1 or supply 0 net. This is a supply net, right? It is not like a yeah, this is also a supply strength, but I want a supply 1 net. So this, but I want to assign supply 1. I want to assign supply 1. Is it supply? It is assigning 0. This is assigning 0, right? And by default, if nothing is mentioned, right, it is supply 1. By default, if nothing is mentioned, it is supply 1. Okay. So this is the proper supply 1 net. Here, although this is written supply 1 and 0, these are just telling the strength. Actually, I am assigning 0. So this is not the correct option. Okay. So supply 1 will be correct, and this is, we are assigning weak 1 and 0. So of course, this is not correct. We are not assigning weak strength, we are assigning supply strength, right? So this is also not correct. So let's move on to the next question. So I will delete this page. Yeah. What is the behavior when two drivers pull one strength drive a war net with values 1 and z? So if I am driving 1 and 0 and z, right, of a word net data type, it will be simply 0, because like this is, you will say, sir, it will be the OR of high impedance and 0, but high impedance, right, it loses its state whenever I try to drive some other value, because it has the least strength, right, if you remember. So it loses its strength, simply it will be 0. It will be simply 0, no question about that. I think we have done a problem like this as well. So let me delete this thing. Yeah. So which of the statements about WANT net it's true? If all the drivers are 1, the net will resolve to 1. Yes, this is true. If any of the driver is 0, the net will resolve to 0. Again, this second statement is also true. It models a wired OR connection. No, it models a wired AND connection. It defaults to Z if no driver is connected. Any wire data type will default to Z if nothing is connected. So option D will be correct. Okay. So next, right, is this one. Which of the following code snippets creates a WAND net that resolves 1BZ? Okay. So this, right, does it creates a snippet WAND net? Okay. So assign net, it is a WAND type, as I am assigning 1BZ. So this is 1BZ, this is 1Z. So all of them actually assign high impedance state. So the answer will be all of the above, like there will not be much difference. Let's do this next question. Create a scenario where two drivers of strong 0 and weak 1 drive a war net. What will be the output? Again, simple logical OR. It will be 0 or 1, that is 1. So option B will be the correct answer for this question. Pretty simple questions. Okay, now we will understand about modules and ports. Okay, so although we know better about models, we will dive more deeper about models. A Verilog module is the fundamental building block in digital design. Each module has various optional and required components, which can be defined in any order except for the module and end module keywords. So order can be anything except for the end module and module keywords, because everything happens in concurrent nature, right? So that's why order can be anything. So the first thing is variable declaration, like it can include wire, range and other data types, as we have discussed. Lower level module instantiation. Inside a module, I can have another module instance. Okay, we will discuss about module instance as well. Enables us hierarchical design by reusing the smaller modules within higher level modules. We'll see few examples of this. Then port definitions, interfaces basically. So it has some inputs, it has some outputs, right? So it needs to have port definitions with external interface, external signals. Behavioral statements written in always or initial blocks. We'll understand what is always and initial blocks later on, don't worry about it. Data flow statements like assign keyword. Okay, we have already learned what is assign keyword, used for continuous assignment in combination logic and task and function. So although we have done all this, still, like, now we will actually understand what a module is. So only thing that is mandatory in module, right, only thing that is mandatory in module is the module keyword, module and end module keyword, and the module name. Okay, this module name of the module. So the ports, right, they're optional. It can have some inputs, it cannot have some inputs, right? But these three things are mandatory. Okay, so yeah, that is what we learned about module. So example, next we will discuss about a SR latch. Okay, so let's consider an SR latch with various inputs. I hope you know what is a SR latch. Okay, we'll try to code that SR latch, right? What is SR latch? This is the hardware of SR latch, right? We have two NAND gates. This is S bar, this is R bar. and this one of the input is connected from the output of the other NAND gate and the other one as well. Okay, so this is the this is a module for a SR latch. So inside the module I call another module, that is NAND gate, that is also another module, right? We call lower level module instantiation, because if I write this NAND gate code inside this module will be very crowded. I don't want that. I want the user to understand what am I doing here. Okay, the NAND gate functionality will be taken care inside the NAND module. Okay, I don't want to show that to the user. That is the power of modules. Okay, so I hope you understood a basic module of SR latch. We'll code this SR latch later on as well, don't worry about it. Okay, next is ports. Ports, I have explained you previously as well. Ports are interface that connects a module to its external environment. They facilitate communication between module and other modules or the test bench. Okay, so there are mainly three types of ports. One is the input port that is used to receive signals. Okay, another one is the output port that is used to transmit signals. Bidirectional ports, that acts both as input and output. One thing you have to remember, that this is the input, this is the output. There are a few bidirectional signals that act both as input and output. I have told you previously as well that your input signal must be wire. Okay, because input must drive this module, right? It has to drive. That's why it must be of wire data type. Output can be reg or wire. There is no boundation on output, but if we are using the output inside a always block, it has to be reg. Okay, these things you have to understand. Like there is a visualization as well. I will show you that visualization. With that you will understand this better. Okay, there is a visualization that will come later on. So here let's read these points. All ports must be declared explicitly in the module. Okay, they must be declared in the module, right? If they are not declared, how will the Verilog understand it is a port? Input ports are always of type wire. Output ports are implicitly wire but can be declared as reg as well. What does implicitly wire means? If I don't say anything, internally Verilog understand it is of type wire, but if I want it to have type reg, it is possible, but I have to write here output reg. Okay, if I write here output reg, then it will be of the type output, it will be of the type register. Okay, so this is how we define, like this is a full adder, this is the input and output ports of a full adder. That's it, right? I have not defined the functionality, just I have defined the input and output ports. Okay, you can write this any order you want, but remember when you will do the simulation, right, when you will design the test bench, you have to follow the same order. Okay, or you can use that dot sum like that, which I have explained previously. That also I will discuss in the next few slides. Okay, or in the next lecture, I don't remember exactly when we will discuss that. Okay, so module of a bidirectional buffer. Okay, so this is like full adder, and inside these are the inputs and these are outputs. As you can see the ports, like this is coding a bidirectional buffer. So input wire is enabled to enable the buffer, in out is data bus. Okay, so it is a bidirectional buffer, so the data bus will be a input as well and will be a output as well. Alright, okay, input wire data in, output wire data out. So what we do, data bus is equals to, this is a bidirectional bus, enable. So if enable is high, it will choose the data in. If enable is low, it will choose high impedance. Okay, that is what we do. Assign data out as data bus. So ultimately output is assigned to data bus. Okay, so yeah, I hope you understood this point. Data bus acts as a bidirectional port driven only when the enable is high. Okay, this operator, right, I will explain later on. This operator will be cleared later on, don't worry about this. And when enable is low, the port is set to high impedance. Okay, I hope you understood. This is like a what do you say, simple ternary operator, right? So you can understand this. Now we will discuss about connecting ports, as I was explaining, right? Exactly, this is what I was explaining. There are two ways to connect ports. One is the ordered list, other is the named connection. So this is where the signals are connected based on their position. So if I have defined my module as sum cout abc, so if I write here whatever first variable, right, that will be equated with sum in the module. Okay, if I write here cout, then cout will be equated with module, as I have shown you examples, right, with our adders. Okay, half adder and full adder as well. But let's say like this is very daunting, right? We can mess up. We have to ensure that the order of the signal matches with the module definition. But let's say I don't want to do that, right? I don't want to be in that mess. Okay, so what do? We have named connection. So here what we do, signals are connected using the port names, providing flexibility and clarity. So it doesn't matter which order I write. Simply if I write dot c out, so this, right, is this dot c out. So whatever is inside this curly brackets, this gets initialized with C out. That's it. That's it, right? Now I don't have to follow any orders. Named connections allow ports to be connected in any order, and unconnected ports will be simply omitted. Okay, they will be high impedance. Now let's come to the important. This is an important thing. You like must remember this. Although I have explained this previously as well, but this is very important. Okay. Inputs, port connection inputs. Input must be of type net internally. So internally inside the module it must be of type net. Okay, but externally it can be reg or net. But input it must be inside the module itself, it must be net. So here it must be of net data type. This is the input, right? It must be of net data type. It will not be reg. It will throw error. I'll show you examples while live coding. Okay. But externally it can be reg or net. Outputs can be reg or net internally. Output internally can be reg or net, but outside it must be a net because it has to drive. That is why output must be a net externally. In out always has to be net type internally and externally because it has input and output. So this has the foundation to get net outside. This has the foundation to have net inside. That's why it takes the lower value, that is net, both sides. Okay. With matching, it is permissible to connect signals of different widths, though winding may be issued. So this is not useful to us. We won't care about this. And unconnected ports. Verilog allows ports to remain unconnected, useful for debugging or unused ports. Okay, the ports can be unconnected. They will be high impedance. That is possible. Or if they are of net data type, they will be high impedance. If they are of reg data type, it will be X. Okay, so Verilog supports ANSI C style port declaration. Like basically this is the port declaration. Where like I can directly inside these brackets as well, I can declare the ports. Up until now what I was doing, I was just defining the variables, and inside the module I was defining the ports. But you can declare the ports here as well. There is no foundation. You can declare the ports here as well. Okay, whichever way you find suitable, you can do that. Now we will understand about module instances. Okay, a module is like a blueprint or a template, right? That defines the functionality, inputs and outputs of a design block. Let's say it is an adder. How it will perform the addition and all those things, that is defined by a module. However, to use a module in a design, it must be instantiated, just like a variable, right? If I want to store a value to a variable, right, I have to instantiate the variable x equal to 4. Then I can use the variable x. Same as module as well. First I have to instantiate the module. The process of creating a usable object from a module template is called instantiation. The created object is called instant, just like this, right? This is a module instance. I am creating a module of type full adder 4 whose instance name is FA ordered. Okay, so I hope you understand that point. Nesting of modules. Verilog, each instance must have unique name in the design. This is a very important point. Each instance must have unique name. They cannot have same names. Two modules cannot have same names. Then your Verilog will throw an error. Okay, if you want to find out bit of similarities, right, you can find similarity like functions in C. If you have studied C, you will understand this, functions in C. Okay, but here what we are doing in C, it was just a function, it was just a code, but here it is actual hardware. It is a hardware. Okay, and this is just like calling a function, right? I want to call a function, so we have to instantiate the function. That's why call a function in C. Just I am giving you a bit of analogy between C and Verilog. If you don't know C, ignore this part. Okay, so one more thing that C allows but Verilog doesn't allow, nesting of modules. That is, Module inside a module. Verilog does not allow one module definition to be written inside another module definition. Modules must be defined separately and then instantiated to achieve hierarchy. Basically, one module is here, right? It is one module is here, module X. Some inputs are there, some functionality is there. Then again inside this module, I am again defining module Y, okay, and then end module is there. End module and then again end module. This is not allowed. This is not allowed. Okay, so similar to C, like C also does not allow nested functions, right? Same as here, but C has one concept named recursion, but I don't think we can use the same recursion concept here in Verilog. Okay, so these are few model instances. This is a T flip flop. Don't worry, we'll understand T flip flop later on as well. Like we'll model flip flops later on. Okay, so this is a basic module. Okay, in this module it is calling a D flip flop. We can make a T flip flop with a D flip flop. Okay, so D flip flop will be defined somewhere else and I'm calling a D flip flop. So basically this is a hierarchical like module instances, right? Hierarchical module instances. Okay, so that is what we do. Like a T flip flop can be implemented with a D flip flop and a or XOR gate and clock basically. Okay, so yeah, that's basically about the T flip flop. Ripple counter also you can see. Ripple counter, like basically if you want to design a ripple counter, right? If you want to design a ripple counter, we can call it T flip flop, but like we can design using a T flip flop. I will not explain the ripple counter right now, but what we are doing here, right, this is wrong. We are first defining a module named ripple counter. Inside the ripple counter we are defining another module named T flip flop. We cannot do this. We cannot nest modules. Okay, we cannot do it, although we know that yes, if I want to design a ripple counter, we can design it with T flip flop. We'll come to that later on, but I cannot nest it. I can instantiate this module and define this T flip flop module somewhere else, but I cannot nest it here. Okay, so just few important points to note. Verilog supports a hierarchical design methodology where every module instance, signal or variable is identified by unique name as explained previously. Hierarchical name referencing enables the use of a fully qualified name to address any identifier. I will explain what this means. I will explain. The name is formed as sequence of identifiers separated by dots, representing each level of hierarchy. What does it mean? So, like I think here we have few examples. Where is the example? Okay, this is not here. Yeah, this one. Okay, so let's say inside stimulus we have a module instantiated as M1, which is a SR latch. Okay, and this is the highest level of abstraction. Inside M1 SR latch, a module is instantiated named N1, which is a NAND gate basically. So I can call directly this module like stimulus.m1.q. Okay, q is also inside this, so I can call this, like if q is this module, right? Q is this module. I can directly call this .q. Like this will be the value. Q will be the value. I can call stimulus.m1.q bar. I can get the value of q bar. I can call stimulus.m1.s. I can get the value of s from this module. I can call stimulus.m1.r. This basically means give me the value of r inside the module m1 inside the stimulus module. That is what this means. Okay, so these are identifiers in the instance m1. These are the root level identifiers. Stimulus.q. Stimulus.q is here, right? Inside stimulus as well there is a value q. So if I want to get that value, I will write stimulus.q. Stimulus.q bar I will get here. Stimulus dot all these values I will get here. Okay, I will show you with examples. Don't worry about it. Stimulus.reset is here. Okay, so if I want to get into the gates of n1 and n2, right? Get the outputs of n1 and n2. Simply I will do stimulus.n1, stimulus.n2. Okay. So yeah, I hope you have understood these things. Like this is what is written here only, simple structural things. I will explain this with code. Don't worry, in the code I will explain this. But what are the benefits of hierarchical naming? The benefits of hierarchical naming is unique identification. I can uniquely identify any module anywhere, right? Simply if I do dot dot, I can uniquely identify where, okay, R is here, S is here. That's the advantage. Debugging and tracing. Sometimes we need to trace where the error is coming from. And scalability. It is so scalable, right? You can insert again another module It is very scalable. That's why the advantage of benefits of hierarchical naming. Okay, so now let us move to the code. So I will show you the code. Okay, so if I just show you the code, okay, the code is again, okay, code is now showing. Okay, fine. So this was the previous code actually, but I have to open the new code. So if I open the new code, just give me 1 second. Yeah, so the new code is opened. Okay, so now again I have to do cd because the file is new, so location has also changed. Again I will do cd. So first of all I will do cd here, cd to the new location. Okay, so I have done cd. Then what I will do is I will first show you the code. This is the test bench. Okay, this is the test bench. Here what we are doing, so first of all, right, I have to show you the invalid what you can say, the invalid input output ports as well. I have to show you the port rules as well, right? So that is what I wanted to show you. So if I go back to the this one, right, if I go back to my where is the port rules, the port rules is here. Yeah, so my input, right, so what am I doing? I'm doing this ports check currently. Okay, so this one should be okay, this is ordered. So where was the ports? I just wanted to check one thing. Okay, that is later on, ports ordered and on. Okay, this is later on. So this one, right, I will cut this one should come here first. Okay, so let me I'm instantiating the ports rule. So where is the ports rule? Ports rule is somewhere here. So I will cut this and this will be here only. Okay, this will be at the starting. So if I just uncomment this ports rule, now we will try out different things, right? So sum, right, sum is a output, C out and sum is the output, A and B and C in are inputs. So currently this is all wires, outputs are wires, inputs are also all wires. Okay, so now if I compile this code, will it throw an error? We want to check that, will it throw an error or not? That is what we want to check. Okay, so the inside internal the module as well, everything is wire, everything is wire. Okay, every single thing is wire. Okay, now if I compile this code, to compile this code again I have to change the names because this is a new file. So the file name is modules ports, but here, right, you have to write VVP because this is where I will store the output. Then I will write dot backslash modules test bench, right, because I am compiling the test bench. Okay, test bench is calling the modules port file. I press enter. No, it is not throwing any error. Okay, not throwing any error. Of course I am not printing anything, so it will not display anything as well. Okay, but now let's do one thing. Let's change the outside input, right? If I change the outside input to be rich, sorry, not the outside input, if I change the output to be a rich data type, if I change the output to be a rich data type outside the port, is it possible? Is it possible? So where did it go? Where did the thing go? Okay, this was actually previously. So this, right, is not allowed actually. So if you see now, if I compile the code, right, if I compile the code, this is throwing an error. Port 1 sum, port rules must is sum, right? Output port expression must support continuous assignment. That means it must be of wire data type. It cannot be of reg data type. Like, let me come back to my tablet. So here, right, I have explained you this thing, right? Output must be of net data type. It cannot be of reg data type, as Verilog is throwing up some error. Okay, so now if I again go back to my VS Code again, now I will check this one. Input must be of net data type, right? If input is not net data type, then it will throw up error inside the module. So I have to go inside the module. Now this is outside the module. So I will comment this one out because this will anyways throw out error. Okay, I will uncomment this one. And now what I do, I will change the input to be reg. Previously it was var, now the input is reg. Will it throw an error? Let's see. Okay, so now if I compile this again, it throws an error. Like net data type requires system verilog. So system verilog. Okay, sorry. Okay, sorry, I was not showing you the screen. So like what I did is simply I commented this line, okay, and uncommented this line. because this was the previous code and only, and I commented this line and uncommented this line. Now my input is data type, and if you see that I'm getting an error here. What is the error? Net data type because system Verilog. Don't worry about system Verilog, but just understand this, that it is not valid for Verilog. Okay, we cannot use this for Verilog. Again, I will comment this one out. And one more thing we know is that our output can be rich inside the module. It is valid, right? If I show you the notes again, if you see the notes, output can be rich inside the module. It can be rich on net data type. It has both options. So if I again show you the code, so here if I compile this, right, it will not throw up any error. Okay, it will not throw up any error. It directly compiled. So that is what we understood from this one. Few these things also I forgot to mention. This one, right, this ordered and unordered. So I will discuss about this one as well. So if I paste this, and this ports check should be actually somewhere here. Okay, this top module will be after this. We'll discuss about this later on. Okay, so like this, right, again, like I have explained this previously as well. If I have a full adder, okay, and if I'm now, let me comment this one out. This one, the task of this is done. So let me uncomment this one. Okay, full adder I'm checking. Okay, so this is FA ordered. Where is FA ordered? Okay, FA ordered is not here. Actually, this module name needs changing to be FA ordered. So, okay, am I calling full adder for anywhere else? Okay, no, that is fine. Yeah, so this is the same model only. Yeah. So what I was telling is that now the order matters, right? Order matters. So like, of course, I don't have any display statements here. You will not be able to understand. So if I like write this thing, right, so let me assign here, these are all wire data types, so I can assign sum equals to any value, okay, any 4-bit value. So I will assign it binary 1011. Okay, like I'm not doing actually sum, I'm just assigning it something, anything. Okay, for now, just to show you something, just to show you. And cout is a 1-bit number. I can assign cout equals to, it is a 1-bit number. Okay, so it will be 1B1 I can assign. Okay, and AB or anything, AB are the inputs. I don't care about the inputs right now. Okay, so now if I display the sum and the outputs. Okay, so now if I display here, it must be inside the initial block, initial begin. Okay, don't worry about this initial begin and end. I will take care of this later on. So it will be display sum percent 0b. Don't worry about this percent b. I will explain this also later on. Cout percent 0b, comma, this will be this will be comma sum and cout. Yeah, so this is fine. Okay, so now if I want to like if I compile this code, okay, this ports check must be commented out. If I compile this code and if I see the output of this code, right, VBP modules port VBP. Okay, you see that sum has 1011 and cout has 1. Okay, so like there will be a bit of confusion. Like let me make all these 4 bits only, else there will be a bit of confusion. Okay, 3:0 and this also 3:0, else there will be a bit of confusion. Okay, now what I will do, like this, although I have explained this previously as well, let's say I messed up in the ordering. Okay, I have written this cout first, then this sum, then the output also will be weird, right? Output will be swapped. Okay, you see that sum is getting value 1 and cout is getting value 1011, but this is not desired, right? I don't want this. To rectify this, what we do this. Okay, I can put this after this. To rectify this, we call our modules, instantiate our modules like this, dot cout dot sum. So even though the order is messed up, right? Even though the order is messed up, but Verilog understand that I have to go inside dot cout and give this value name, okay? So now if I compile this code, you will see that exactly what I was expecting, I'm getting that. Sum is 1011 and cout is 11, okay? So that's how we call with dot, right? With dot we call different modules, okay? So this is how I hope you have understood the previous thing that I was explaining about ports and modules. Now let's come to this example, SR latch and all those things, okay? So let me comment these things out. These are not important anymore. Okay? Now let's instantiate the top block. Let's discuss about like this modules and hierarchical module, okay? So this is like ANSI, see how you can describe modules. So this is done. This is the SR latch, okay? Now let me uncomment this out. So these are like this is SR latch. Inside this I'm instantiating another lower level modules, that is NAND gate. So this NAND gate N1 and N2, they are doing some manipulations and then they are calling it, okay? So this is the top module. Inside top module I have this wire. Inside this I am calling SR latch, then again this SR latch in turn is calling some other modules, okay? This is how hierarchical modeling works. Now if I run this code, okay, if I run this code, what will happen? This is just SR latch, okay? There is some syntax error, 24, okay? This should be commented out, yeah. So now if I run this, yeah, now if you see, like at time 0, I'm giving, like I have some monitor statements, it monitors it changes. I'm giving it S and R to be 0 0, then in the latch I'm getting X. Initially it doesn't have any value, so it will be X, okay? Then I'm getting S0 R1, so it will be reset, so that's why Q is 0. Then I'm giving S1 R1, again it is set, this one S1 reset 0, that it is set only 1, okay? So you know, like the truth table of SR latch and all those things, you know, okay? I'm not here to explain you that. Okay, so I have made few changes to the code to explain you this thing, right? Let me go back to my tab to explain you this stimulus.m1 and all those things. To understand that, I have made this changes to the code. So if I see in the code itself, right, that what I have done, instead of printing the values here, right, I have commented this line out and I am printing it here, okay? So what is the advantage? Advantage is I can access the module variables outside the module if I have an instance of that module. So here I have instance of this module MUT. So if I do mut.set, basically what it tells me that go inside this MUT module and check if I have any set variable. Yes, I have a set variable. So it will simply print the set variable. Then go inside this MUT, check if I have any reset variable. Yes, I have a reset variable, simply print that. Then again where Q is there, right? So go inside this module MUT and check if I have any Q. Yes, Q is there, so it will print that variable. So if I just run this code, okay, you will see the output is same as the SR latch that was expected. Now let's say if I want to store this value, that is also what we can do, right? Outside, if I want to store this value, we can do that. So I'm initializing a array, and now, right, I'm storing some weird value like this. Inside this MUT module, I have this module M1. So I can go inside this M1 module and store the Q bar value. So if I go inside this M1 module and store the Q bar value, okay, I can do that. That is totally allowed. I can do that, okay? So this may be useful in some cases, right? If I want to get this, like, so if I want to go inside this module, then go inside this, right? That is what hierarchical modeling is. So I am going inside this top module and then again going inside the SR latch module M1 and getting the variable Q bar on the test bench. Just see how much long distance I'm going, right? Still I'm getting the value Q bar, okay? So if I try to print this, you can print this. This will not throw out any error, okay? This will print out. So if you want, let's say, if you want value Q, you can get the value Q as well. So just change this to Q, okay? And you will get the value Q instead of Q bar, okay? You will see you are getting the value Q instead of Q bar. Basically, it is the opposite. It will be just the complement, right? Now let's see if I can get an input as well. If I can get the input value, okay, let's check that. So you cannot go inside the NAND gate because the NAND gate, right, is like a primitive, so I cannot go inside the NAND gate, okay? So if I just show it as S bar, can I get the S bar value? Yes, I can get the S bar values as well. Okay, so any variable you like, you can show it here. Okay, you can get from outside the module. Just you have to use the dot operator. Okay, that is how you. These are known as identifiers. Identifiers. Okay, in of module instances Okay, so that's basically it for this lecture. I will just like go back to my tab. So that's basically it. That is what I wanted to explain to you. What are the identifiers, different things. So this is the advantage. This is the power of hierarchical naming and modules. Okay, so I hope you understood all the things that we explained in this lecture. So in the next lecture, basically we'll learn few more topics related to simulation and test bench. So up until now, what I've been doing, I've been using a test bench, I've been simulating, but I have not explained you how does a test bench work, how does a simulation work. I have just told you to skip it. So in the next lecture, we'll learn about that, and we will design a 4-bit ripple up counter. Also, we'll understand initial, always, and begin and end statements. All those things we'll understand in the next lecture. Thank you for watching. If you learned many things, make sure to like the video, make sure to comment the video, and I hope to see you in the next video. Until then, happy learning.